So what I would like to do today is to show you some idea how to try to shed some light on the difficulty of integer linear programming or combinatorial optimization. This is a joint work with Jörg Bader, who is a doctoral student, Rob Hildebrand, who was our postdoc, is now at IBM, and then my colleague Rico Zenklusen. Actually, I should first switch on this thing. It's already on. So, the way I would like to start is the following. This is a little introduction to integer linear programming for those of you that have not seen this before. So, maximize CTX, AX less or equal to BX in Zn. No nonlinearities, no polynomials today, nothing. Just the classical setting, which is, of course, an NP-hard problem. And what we would like to do is now the following. That's the usual setting. The first thing is you try to relax integrality on the variables and go to the LP. Now, what we would like to do is something a little bit different. We would namely like to parameterize the problem in the following way. So we want to add a few hyperplanes. So the W matrix, the rows consist of these normal vectors. And now we want to add Wx being integral. And the idea is that we would like to add not so many of these Wx in Zk constraints, but somehow we want to have the k very, very small. That would be the dream. Why do we want this? Now, there are several reasons. Now, clearly, if you do this in each round, instead of solving an LP, you get a much stronger relaxation. That's at least what you could expect. But what I think, what really the beauty is, this is a kind of an attempt to build this bridge from fixed dimension theory in integer programming towards combinatorial or integer programming when the number of variables is big. And of course, if the k would be a constant, we know by Lenstra's algorithm, then we could solve this relaxation in polytype. And note also that if you start off with a, say, 0-1 program, then usually if you introduce these kind of constraints here, then you get a larger range. So if the range would be sufficiently big, then it really makes sense to use this IP theory in fixed dimension. Okay, so that's the kind of setting we would like to do. And so now this is the outline of my talk. I would like to begin with a few examples that show you that sometimes you can do something, and then explain a general construction which explains this kind of machinery, if you like. So this is what I call TU decomposition of matrices. So let me begin with a few little examples. So before we do that, so what do we now want to achieve? So there are, in fact, two kind of things. So the first thing is, if you take this matrix with integer coefficients, then clearly the convex hull of the integer points in P is always contained in this object here. So this is indeed a relaxation. Now, we would like now first to understand when is this exact. So in other words, can we describe the convex hull of the integer points in P not by an extended formulation where all variables are continuous, but in fact we allow here for some few integrality constraints that we add here. And the question is, can we do that? And how can we do that? And what is with the k in relation to n? So is the question, I hope, is clear. So if we manage to do so, then of course we have reduced the integrality constraints. And I know from several examples which I have seen, so Andrea Lodi has shown to me some examples where you can write down such a W relaxation that also, at least in various cases, the corresponding MILPs with these few integer variables are really solved efficiently also by branch and bound and cutting plane type techniques. So that might not interest here several people, but in fact, it seems true that sometimes you can really optimize quite efficiently over this relaxation here. So now, let me show you what is going on here. So I started taking this very naive little knapsack problem in 0-1 variables. It fits on the slide. So x1 to x4, and then 4x5, 4x6, 5x7, 5x8 less or equal to 11. So it turns out if you compute the convex hull, you will need 39 inequalities to describe the convex hull. Now, if you look at this problem a little bit carefully, I claim you can describe it by one integrality condition. Namely, take the bigger guys here, so the items with value 4 and 5. Take those folks together and look at the sum of these variables. Now let me request that this sum is integer. So 1, 0, 1, 2, 3 could go up to 4. Then what can we do? Well, we can now take this constraint here, multiply it with 4. So call the result x5 plus x6 plus x7 plus x8, call it z, little z. Now take this equation, multiply it with 4 and subtract it. What will you get? Well, then the 4 here cancels, and the 5 turns into a 1. So therefore, you are left with a beautiful little matroid problem. In fact, it's a trivial description. There's nothing to add. For every right-hand side, this would work. Is that clear? So this is just a nice little example that shows that sometimes if you have some structure, maybe you are lucky. So now parity polytope. This is the convex hull. A second example is the convex hull of all 0, 1 vectors that have an even cardinality support. So this is a little example that shows how it looks like in dimension 2, in dimension 3, in fact. This is the convex hull of exactly these points here. Now, the polyhedral description in the original space turns out to be of size 2 to the n minus 1. This is an old result by Geroslow. Now, you can write down an extended formulation for this problem, which uses 4 times n minus 1 inequality. So it's linear in this extended space. This is a result by Carr and Conjavot. But in fact, you can also write it in exactly the way I said before. Well, by definition, you are interested in those 0, 1 points so that half times the total sum of variables is integral. In other words, you can see this as the projection of the convex hull of xz points. So we introduce this artificial variable z here, such that the sum of the xi minus 2 times z is now 0. But now I request integrality here on the set. This is important, otherwise it wouldn't work. So it's again one of these inequalities that shows how to get to a description. So now, what can we do with this? And this is now the general that's the general kind of approach I would now like to take. So let me look at the following. So let me take the matrix A. This is our constraint matrix from the polyhedron. And now let me make the attempt to write this in the following form. So we want to write it as an A tilde matrix plus a product of two matrices, U and W. Now, W should be integral, and U should be also an integral matrix. But now comes the key property. We want that A tilde W jointly is a TU matrix. So we want A tilde and W together to be a TU matrix, and the U is just some integral matrix so that you can decompose the matrix in this fashion. Now, then the affine TU dimension of this matrix A is just the minimal number of rows of W. Now, why does that make sense? Look, you can take any matrix A here and take A tilde to be the zero matrix, take W to be the identity matrix. And then the U, you just choose A. So you have such a decomposition, but then, of course, since you use the identity, you just use the original variables. That would correspond to affine TU dimension n if you cannot do any better. But the key idea is sometimes you might be better off and manage to find a smaller number of k that allows you to still end up with this kind of decomposition. This is somehow the goal. Now, clearly, matrices with affine TU dimension 0, this is just totally unimodular matrices. This is not a totally unimodular matrix. But this is a so-called almost totally unimodular matrix, which is a matrix which is not TU, but every proper submatrix of A is TU. So if you delete a row or a column, then you have a TU matrix. Now this, in fact, plays a role as a building block for K-balanced matrices. So after my talk, you might want to consult Michele, who can report about this. Yeah, Gerard is also welcome to answer this. Now, these almost TU matrices, in fact, are exactly matrices which have affine TU dimension 1. And this, again, is very easy to see because you can take the full matrix, and now you just split it into one column and the rest. And then you can write this as a matrix 0, A tilde, this is the remaining matrix from A, plus A times, this is now the multiplier of this 1, 0 row here. And now trivially, if you take this matrix together with 1 and all the zeros, this is a TU matrix, of course. So this is an example. And in fact, the matrices with affine TU dimension 1, they have been called nearly totally unimodular matrices in a paper by Gisweit from 2005. And in fact, in this paper, he showed that the corresponding polyhedron has the so-called integer decomposition property. So integer decomposition property means if you take the polyhedron and now you multiply it with a scalar, so you blow it up, k, say you look at k times p, you take a point y there, then you can write it as the sum of k vectors from p. This is this integer decomposition property. So this is what I wanted to mention. So now here comes the observation, which is really showing that we can use that for the study of integer linear programming. And this is if you take such a affine TU decomposition, suppose you have it, and U is an integral matrix, then for all integral right-hand sides B, we have the property, the desired property that if you look at the integer points in P, then their convex hull, in fact, is determined as the convex hull of the points in P without integrality now, but now we request that only Wx has to be in Zk. And that follows from a very basic observation. You can just do the following. Once you have this decomposition with this matrix U, you can do exactly what I tried to show you in this little knapsack case. And you can now look at, so you do the following. You call Wx to be R. So this is now some fixed right-hand side. And you go over all the different R's later on. Now suppose the image Wx is fixed to be R. Then from this decomposition of A, you can rewrite the problem by just writing A tilde x is less or equal to B minus U times R. But now, since A tilde and W are jointly TU, you have the property that for all right-hand sides, it solves. So therefore, the LP optima will automatically be integral. And that's true for every such R. And so the convex hull is indeed the convex hull of the union over all these different right-hand sides that you can now choose. And this is an integral set. So it's even more than you need because you request now integrality on all these fibers. So I call the Wx equals R object always the fiber. So anyhow, I hope that this is clear. And this also holds if you add this additional lower and upper bounds on the variables. That follows trivially from TU matrix theory. Now here is a very nice example. So this is a knapsack problem with this given structure. So this is often called the master knapsack problem. We take n variables, and the coefficients of the ith item is index I. So sum of I times xi less or equal to b. That's the constraint. Now x in 0, 1, n. Now what you can do is the following. So the first kind of attempt is you can directly see trivially that you can go down from n to n divided by 2. Because you can take this master problem here. This is the coefficients, the vector of coefficients, which you can write in this way that you always take here two consecutive items. So two consecutive items have now weight I and I plus 1. They are only off by 1. And those folks you can always aggregate together. That gives you clearly a TU decomposition, and this is just, yeah, if you do the corresponding matrix U, if you work out what the matrix U looks like, then you get exactly this desired decomposition. So this is a decomposition with n divided by 2 rows. Now, in fact, there's a much more intelligent one, and this is one where we can show that you only need 2 times square root of n minus 2 many rows. And the idea is here that essentially, so you can see the following. If I take this knapsack problem, oh boy, I messed up this here because I was cleaning the board. I wanted to be super perfect, but I ruined here all the chalk. So this is how it looks like. So you take this knapsack problem which has coefficients, say, from 1 to k squared. Now what you can do is you group here those folks together in always groups of cardinality k. And then you use here this identity matrix. You use here the next identity matrix, and so on. And you use here the next identity matrix. This gives you k of these rows. So now what you can do is, if you aggregate here in the first, so this is the first block. In the second block, you aggregate all folks together here. And then you do the same thing for the other blocks. And you get a TU decomposition, which has here size k plus k minus 1. So you can work a little bit more, and you get down to 2 square root of n minus 2. So that's exactly what you want. So this is a decomposition, for instance, which shows you that this works very nicely. In fact, what we can prove, if you take a general knapsack problem in 0, 1 variables, then, yeah, the upper bound says we can always do it with at most n minus 2 variables, but we need, in general, at least n divided by 2 variables. So we have an example where we can prove this lower bound of n divided by 2. We don't know what the exact number is, and I think it depends very much on this knapsack structure. But anyhow, it lies in this range of n half divided by n minus 2. Now, admittedly, to go down from n to n minus 2 is not a fantastic achievement, but that's a fact for general knapsacks. This here is a specific knapsack because they have this consecutive coefficient structure here. And this is why you can construct a more efficient TU decomposition. So we don't know whether this is optimum, but we didn't prove a lower bound for this thing. Anyhow, square root of n is good. So now you can do this kind of decomposition. This is just a matrix decomposition. So you can do pretty much the same thing if you replace now, replace a TU-ness by, say, total dual integrality. So you can look at an affine TU decomposition as before. Then the convex Halley is integral for all right-hand sides, B, which are integral. Now, you can ask the same thing. What happens if I give you here this polyhedron with a given fixed B? Now, B should be then an integer. And in this case, you clearly know that then you request that the system AX less or equal to B for the given B, WX equals D is a TDI system for each integral vector D. So here you need for each integral vector D, AX less or equal to B is the given fixed system. And in this case, you can also see that the convex hull of this corresponding WX in ZK relaxation turns out to be integral. So you can replace TU-ness in a sense by total dual integrality if you are interested in a specific right-hand side. And so there's, for instance, an example which I also like, because even though this is a special knapsack type problem, this is now an example where you have this TDI-ness property. Now, TDI-ness property means we have now a given right-hand side. So now the coefficients that I'm using here depend on the right-hand side B. And essentially, we have only 2 blocks of items. So we have the big items, B stands for big, and S stands for small items. Now, big here in this situation means that the weight is between this fraction k minus 1 over k plus 1 times B and B, of course. And small means that the coefficients lie between b over k plus 1 and b over k. Now you can make this exercise, which is a little bit of work. You can try to find the complete description, which we actually cannot, but we can see that the number of inequalities we need in original space is of order n to the k. So k is this parameter which enters here. Huh? So it's n to the k, the number of inequalities. Now you can come up with a TDI description in this Wx integral setting, which has the property that it only uses linearly many inequalities. So in fact, you have here a system of inequalities for every, that is indexed here for every element in the small group. You can write down a simple inequality. I'm not going to discuss here whether this is now the right inequality. You believe me this anyhow. This is the inequality for every element I in S, and you request that the big guys, so this is exactly this thing here, the big elements, they have to be integral. Now, because of their huge weight, in fact, they can only be 0 or they can be 1. That's the only thing that can happen. But if you request this integrality condition, then these linearly many inequalities suffice. And this shows this is a drastic improvement. From n to the k, it goes down to not even n, plus 1 additional integrality condition. So now, the question is now, with this affine TU decomposition, a very natural one is, how would you try to get to such a TU decomposition? And indeed, so when the affine TU dimension is 0, there's this beautiful theory developed by Paul Seymour, by Klaus Trümper on recognition and decomposition of these TU matrices. This is a machinery that we have at our disposal. Now, we cannot, so far, on the positive side, what we can solve is the following. I give you the matrix A, and this is an m times n matrix, and one can decide in polytime if A has an affine TU dimension k, provided that m and k are fixed. So in other words, m fixed means this is like a knapsack problem. I'm not counting these lower and upper bound constraints. I just count the number of non-upper bound constraints. So like knapsack would be m equal 1. And the k is this parameter where we would like to have wx in z to the power of k. So if I fix k, and if m is fixed, we can do it in polytime. And that roughly follows by doing the following. So without loss of generality, you can go to the case where A has distinct columns. But then what you see is that since the number m that enters into A tilde is now a constant, and the W has k rows, which is also a constant, we can enumerate all master TU matrices that in principle could come up, because they have coefficients -1, 0, +1. So we can write them down explicitly. And once we have this, there are only polynomially many such matrices because of these fixed parameters here. And then what you need to do is you have to solve a system of integer equations. So now you still need to find this decomposition with a matrix U. But if you look at this decomposition, then A is now given, A tilde, and W we have guessed. So we have it also at our disposal. And now we have to solve for a U, which gives us equality here. And that means every row of U needs to be an integral solution vector to a system of m linear equations. But we can solve equations over integers. I'm not speaking about linear Diophantine equations, not about non-negative integers, but this is here general integers. We don't care on the signs in this matrix. So this is the idea how you can do that. Now, this is what I just, where I just indicated how to do this. Now, on the other hand, this parameter k, so now here we did two kind of fixing, so the m and the k. Now, if you drop that k is fixed, then in order to decide if a matrix has an affine TU dimension n, this is NP complete. So you can solve this recognition problem provided that the k is a constant, but if you allow for arbitrary k, you now want to know is it n or not, then this is NP complete. This is what we can show. Now, in fact, what we conjecture is that one can solve it in polynomial time, provided that only k is fixed and not the m is fixed. But this is a very difficult question. I spoke with Jim Gillin, who also thought a little bit about it, but he also said this is not so easy, because you essentially have to extend this TU decomposition machinery to the case that we have here, also this W matrix, and this is not clear how to do it. So this is why I put this up as a conjecture. So now, so what it seems is the following. So for certain problems, in particular for these knapsack type things, you can gain sometimes quite a bit with this affine TU decomposition. Now, on the other hand, there is this kind of bad problem like matching, which is also bad here. So we can actually prove that you cannot find an extended mixed integer formulation. So view this now as a mixed integer formulation, because I allow for also some explicit integrality conditions on the variables. And then you cannot find a description of the knapsack polytope with only polynomially many inequalities, so that you have a sublinear number of integrality conditions. So you can save on the constants, so it's easily seen, for instance, that you can go down from n to n divided by 2, because you can just take the matching problem, extract a bipartite graph. This is there you have the TU A tilde matrix sitting, and then you only need integrality on the remaining edges. So this way you get down to n divided by 2, if n is the number of integrality variables, but you can only save in terms of constant. But you cannot go down in terms of, say, something like square root of n or something like this. This is on the negative side, which is a pity. It would have been very nice if this were also positive. But still, I think it's an avenue that is worth being pursued further, in particular if you mix it with this polyhedral description. So now Wx integral gives you this mixed integer formulation, and in order to get to a complete description, the hope is that maybe now the description simplifies drastically. And this is why this U matrix, this integral U matrix, this somehow peels off. This peels off, at least in the knapsack case, these high coefficients. This is exactly the trick, and so you end up with a much nicer kind of structure. So that's, I think, all I wanted to say.